Because of the job they're called on to perform, quite a lot of engineering components can only be made in very special ways, using very special materials. Some of these components we recognize immediately, others we rarely see, but all of them have a vital and specific engineering role to play. The fewer parts you have, the better. This means that single units can often have quite a complex shape. In one piece, you may have united many functions. So how does a manufacturer set about making a wide range of metal shapes to the precise sizes, strengths, and surface finishes demanded by the customer? It's a problem that's usually solved by discussion between engineering designers, production engineers, and metallurgists. It's during such talks that production plans are laid down. So it's important to get a fine balance between what the customer wants and what is possible using a particular production technique. The production process finally chosen is often influenced by the material itself and the shape of the final product. One option open is to cut the material from a metal blank. The main drawback is that this is an extremely wasteful way of doing things and usually very expensive. You could always, of course, forge the part. Take a metal blank, usually made from steel, and form it into a new shape by applying great force to it. It's a speedy operation, but the cost of the pressing machines and the running expenses are high, and the range of possible designs and the metals from which they can be made is relatively limited. So you can see that there's a definite need for a forming process which makes a wide range of shapes from a wide range of materials. One technique is to melt metal and pour it into a preformed cavity. This cavity is called a mold, and it has the same shape as the finished article. When the molten metal has cooled and solidified, it's assumed the dimensions of the mold. All you have to do then is knock it out of the mold. It's a process with a long history, and it's called casting. Casting metal dates from beyond biblical times. The technique fascinated the Victorians, who cast everything from railway stations to bandstands, from cannons to elaborate cast-iron coffins. The great advantage, then as now, is that it's one of the quickest routes between an engineering drawing and the finished article. One of the oldest and best tried methods of casting is the one which uses sand to make the mold. To create a solid object by sand casting looks fairly complicated. First of all, you have to make a pattern, and traditionally this is built out of wood. Patterns that are going to be used over and over again may well be made out of cast iron, aluminium alloys, or fiberglass. But the traditional wooden patterns are made from yellow pine or mahogany. Wood doesn't cost very much, and it can be easily machined and cut. If minor design changes are made, then the pattern can be altered fairly quickly. At this foundry, they make a wide range of engineering components. All of them start life in the pattern shop. It's here that the designer's drawings and dreams are turned into hard and durable reality. There are patterns for everything you can think of. Parts for power stations, parts for North Sea oil rigs. Each piece is unique, and each has its own individual wooden pattern. A British standard colour coding system for patterns shows whether part of the casting is to be machined or not. Red indicates that the surface is to be left just as it is when it comes out of the cast. Black is used to show the position of the sand cores, and yellow means that the surface is to be machined. Other important pointers also appear. The places, for example, where the metal is to enter and rise in the mould through the runners and feeders. The finished patterns, which are made slightly larger than the casting to allow for the contraction that occurs when the molten metal cools to room temperature, have to be coated with a special varnish. This cuts down the amount of moisture absorbed by the pattern from the damp moulding sand. These fiberglass patterns are mounted on a wooden board, and they represent two halves of two separate track links for an earth-moving vehicle. Two large shell-shaped wooden pegs are placed on the pattern together with a hollow fire-brick tube. It's through this tube that the molten metal will run into the mould cavity. It's called a runner. The two wooden shell-shaped pegs will ultimately form cavities within which the molten metal will rise when it's been poured. These are called feeders. The next step is to lower a metal moulding box onto the board and fix it securely and level with wedges. A number of metal bars are fixed across the box to provide a support for the sand, and these are wired firmly into position. A chalk-like parting powder is sprinkled onto the surface of the pattern. This helps to prevent the sand from sticking to the pattern when the time comes for it to be removed. The next stage is to add the moulding sand. This is known as green sand because it's used in a damp state. It's not just any sand, but a special sand which can stand up to the high temperatures involved. It must also be able to retain the shape of the pattern, allow the gases from the molten metal to pass through it, and, perhaps most important of all, the grains of sand should be fine enough to prevent the metal from penetrating the walls of the mould. The sand is rammed firmly into place so that it makes a good contact with the pattern. Then comes another layer of sand until the pattern is covered to an adequate depth. Metal rods called lifters are then suspended in the mould box, and they help to provide a rigid framework for the bulk of the sand. They're rather like the reinforcing bars used in precast concrete. The feeder head cores are held in position with more facing sand, which is rammed firmly into place. To make sure that no unwanted sand enters the mould cavity itself, the central runner is extended and blanked off. When the framework is complete, the bulk of the backing sand is added. It's literally thrown into the box by a sand slinger. You can see by the sparks flying the force with which the sand is entering the box. It's at this stage that the feeder cavities are extended by raising the wooden shells. The final ramming and leveling of the green sand is done by a pneumatic rammer. A peg in the runner and the feeder patterns can now be carefully removed. Then the edges are trimmed with a trowel. The box, with its great burden of wet sand, is extremely heavy, and it has to be fixed very securely to the pattern board. The next move is to get the pattern out of the mold box, and this is done by simply turning the whole thing upside down. It's here that all the careful work in preparing the mold proves its worth. If the whole thing fell apart now, you'd be back to square one with sand on your face. The pattern and its mold box are turned over carefully. And after the fixings are removed, they slowly part company. Remember, this is still only one half of the final mold, because it only contains the impression of half of the two single track links. This is actually the top part of the mold, and it's called a cope. Small steel nails, called sprigs, are pressed into any parts of the mold which are likely to break away during the pouring of the molten metal. And then he removes a loose piece. This is followed by a final trimming of the mold cavities. Next, the surface of the cope is covered completely with a fine alcohol-based spray. This is then burnt off, leaving the surface of the facing sand hard and dry. It's now ready to meet up with the bottom half of the mold. And this is the finished bottom half of the track-link mold. It's called the drag, and it's been prepared in an identical way to the top half, the cope. Many castings like this track link incorporate internal details which are difficult, if not impossible, to machine. It may also be technically difficult to allow for these when the pattern is being made, because you wouldn't be able to remove a really complex pattern without damaging the mold. This presents a problem, but to every problem, there's an answer. The answer here are cores of sand which have been mixed with a binding agent like linseed oil and baked in an oven. The core positions are marked clearly on the pattern, and they can be fixed easily into place. Next comes the positioning of what's known as denseners. These particular ones look like small springs, and they're there to make sure that the metal solidifies uniformly throughout the mold. To ensure that the cores retain their correct arrangement, core prints are glued into place. Finally comes the positioning of the chaplets. They look a bit like old-fashioned shirt studs, and they're there to prevent the cores from moving when the metal is poured into the mold. When all these bits and pieces have been fitted into place and checked, the drag finally unites with the cope. They're firmly locked together, and the completed mold is now ready to receive the molten metal. The steel that's going to be used to make the track links is melted in an electric arc furnace, which is ideal for using cold charges of scrap and leftover feeder heads from previous castings. After testing to see that the steel is of the right chemical analysis, a probe is inserted to check the temperature. When this is right, the furnace is tapped. Because this is a jobbing foundry, the batches tend to be small. The track-linked mould is just one of a number of different moulds to be cast from the same ladle. Obviously, only moulds demanding metal of that particular chemical analysis will be poured from that ladle. Quantities poured will vary from mould to mould. At this stage, a powder is added to the mould to prevent the metal from cooling too rapidly. The metal is poured carefully into the mould until it begins to rise in the feeders, revealing that the cavity is full of molten metal. Although a great deal of excess molten metal may be used, up to 50% more on some occasions, there's no wastage because it can always be melted down and used again. The excess metal is needed to compensate for contraction during the solidification process. The completed casting is allowed to cool in its box. When it's cold enough, the sand and the casting can be removed from the box. This is done in the shakeout area, and here the casting and the sand part company. Sand goes off to a reclamation plant where it's cleaned, ready for reuse in the foundry. Of course, the casting isn't yet in its finished state. The runners and feeders are still attached to it like umbilical cords. These are removed by cutting and burning. The final stage is to assemble the track after it's been given its heat treatment. For one-off jobs and small batches of up to 100 components, sand casting is ideal. But for long production runs, making workshop vices like these, for example, then the economic answer is the automated foundry. The moulds, which are made from green sand, are turned out at the rate of 240 per hour. The addition of resin-bonded cores is the only hand operation needed. The mould is boxless, and so the green sand must have a high compression strength, twice that of the sand used in the traditional foundry. And it mustn't be too damp, otherwise it could easily disintegrate. The completed moulds are passed to the continuous pouring station on a conveyor. The station has two ladles. While one is pouring metal, the other is being charged with metal from the furnace. Each ladle can hold 6 tons. In this case, it's molten grey iron. The whole process is carefully monitored, and any malfunction in the moulding or casting cycle brings the conveyor to an immediate halt. For this particular casting, each mould weighs just over 24 kilograms, and the finished casting just over 17 kilograms. This gives a yield of 70%, which is considered a fairly high one in this business. Still on the moving conveyor, the moulds are allowed to cool in their own time. Because there's no moulding box to worry about, the noise level in the shakeout area is greatly reduced. The casting is still complete with its runners and risers. It says goodbye to the sand in this rotating drum. The sand simply falls through a series of holes, allowing the casting to continue on its way. After processing, the sand is recycled into the system, and the casting is carried to the finishing area. The runners and feeders are removed from the castings, and away it goes for shot blasting and finishing. Automatic sand casting is an ideal method for producing large numbers of relatively uncomplicated castings. But the more traditional method of sand casting is ideal for complex components which may demand a variety of different high-melting metals. This traditional technique is used to make over 70% of the castings produced in Britain. But it does have its limitations when large numbers of a single component are required possessing high tolerances. There's no doubt that it's a time-consuming and expensive business having to make a new mold every time you need a new part. So, provided the melting point of the metal isn't too high, then it's much more desirable to use permanent molds. We'll be taking a look at that particular production method in a later program.